So, hello guys, welcome to this part one episode on matrices, right? We'll be focusing on the concept of a matrix, formalizing a matrix, and the types of matrix, right? And remember that making excuses will never get you anywhere, okay? Let's get into the lesson. The concept of a matrix. So here we're going to look at what is a matrix. So a matrix is a rectangular arrangement of elements, and elements here could mean numbers, letters, things, symbols, etc., into rows and columns. So it's a rectangular arrangement of elements into rows and columns. That's very important. And these elements are usually expressed in a pair of curved or squared brackets. Now, take a look at the example down here. Let us put that into perspective. So a matrix is a rectangular arrangement. Now, we say rectangular arrangement because the elements, right, these letters here, or whatever is inside of the curve or squared brackets, we call them elements, right? These could be letters, words, symbols, numbers, you know, etc. So these elements are arranged in a rectangular fashion, right? Just look at this here. So they are expressed in a rectangular fashion, right? Can you see that? So the pattern that the elements form is a rectangular pattern, right? So that's what the definition is saying, that a matrix is a rectangular arrangement of elements into rows and columns, usually expressed in a pair of curved or square brackets. Now, there are two examples here, just two different ways of expressing the matrix, right? In this example, right, we are using a pair of curved brackets, versus in the other example, we're using a pair of square brackets. So both ways are acceptable. And if you see a matrix being written using curved brackets, it is just as correct as someone who is using squared brackets, okay? So whether curved or squared brackets, both are acceptable. Okay, guys, let's move to the next point. So rows, so remember we said that the elements are arranged in rows and columns. So how do we identify rows? Rows run horizontally from left to right. So rows run horizontally, right? So that would be our rows. Rows are horizontal from left to right, while columns run vertically from top to bottom. So columns run vertically, right? From top to bottom. So let's look at the matrix here now. So obviously you can see that the elements A, B are in a row, right? See, they're in a row, right? They're going in a horizontal fashion, right? They're going in a horizontal fashion from A to B. So AB is in a row, as well as CD. So CD is also in a row, right? So we can now identify the elements that are in rows, right? And in terms of column, it therefore means that BC would be in a column and BD, sorry, so AC would be in a column and BD would also be in another column. So it therefore means that this matrix has two rows and two columns, right? So rows run horizontally and columns run vertically, right? And the elements must be written such that you have space between them. Now you're not going to see the elements in literal having lines separating the rows and the columns. Within the matrix, the rows and the columns are separated using spaces. So when you look at the elements, you should be able to tell which elements are in what row and which elements are in what column because of the spacing that is there. Okay, so bear that in mind, guys. All right, so a capital letter is usually used to name a matrix. So we often use a capital letter to name a matrix. Now, that doesn't mean that the matrix has to have a name. The matrix could be nameless, right? However, for representation, we can name the matrix. We can give it a name. And to name it, we normally use capital letters to name the matrix. So in this case, this matrix would be matrix A, right? So matrix A would be equal to ABCD matrix here. All right. In terms of naming the matrix, I normally associate it to sets. I mean, you guys should know about sets, right? And, you know, we normally use capital letters to name sets as well. But with sets, we use a pair of curly brackets, right? And inside we have our elements, right? So I normally associate the representation of a matrix to that of a set. You know, it's kind of similar in terms of the naming, right? So we can name a set A, we can also name a matrix A. The things inside of this set, we call them elements, and those things that are inside of the matrix, call them elements. For matrices, we use curved brackets or square brackets. However, for sets, we use curly brackets. So it's kind of similar in terms of your remembrance. You can, you know, in terms of remembering, you can make that association, right? So now we're going to move on to the next concept. So apart from knowing what a matrix is and knowing that the elements are arranged in rows and columns, and rows run horizontally while columns run vertically, and that a matrix can be given a name or it can be nameless, we are now going to look at the order or size of a matrix. Now, this is a very important concept when you are doing matrices, the order or the size of a matrix. Now, the order or size of the matrix basically tells the number of rows against column or versus columns that the matrix has. So it tells the number of rows versus columns that the matrix has, right? And mathematically, we express that as R times C. However, it is read as R by C. That is the number of rows by the number of columns. So please remember not to read this as R times C, right? That is multiplication, guys. What we're actually doing is representing the order of the matrix. And to tell the order of the matrix, it is the number of rows R by the number of columns, right? So the times symbol here basically means by. So when you're reading it, you must say row by column, row by column, not times. Okay, guys? So the order, the size of a matrix tells the number of rows by the number of columns that the matrix has. Okay, so let's look at these examples here. So example 1, matrix A. Let us see if we can write the order of this matrix A. So first we need to identify the number of rows that the matrix has and the number of columns, and then write it in the form R times C. Okay, so let's identify the rows. So we can clearly see that AB is in a row and CD is in a row. So those are the only rows that are there. So it means that this matrix has 2 rows. So that's how we get this 2 right here. And then the matrix also has 2 columns because AC, right, is in a column, is in the first column, a matter of fact, and BD would be in a second column. So it therefore means that this matrix would be a 2 by 2. So the number of rows would be 2 and the number of columns would be 2. So this matrix is a 2 by 2 matrix, right? So that's a 2 by 2 matrix. Example 2, matrix B. Matrix B, clearly you can see that P is in a row by itself and Q is in a row by itself. So there are 2 rows, right? And P and Q are right below each other, right? So it therefore means that PQ would be in a column, right? So PQ would be in a column. So there's 1 column, 2 rows. So the order of this matrix is a 2 by 1, 2 by 1, right? And example C, we notice that M, N, and R, right? They are spaced. So it therefore means that they are in different columns, right? However, they are in 1 row. We can draw a straight line across and we see that they fit into 1 row. However, M is in a column by itself, N is also in a column, and R. So it would be 1 row, 3 columns. So the order of the matrix C would be a 1 by 3 matrix, right? So matrix C is a 1 by 3 matrix. Now, let's look at matrix D. So matrix D pretty much has 4 rows because A is in a row by itself, B is in a row by itself, C is in a row by itself, and D is in a row by itself. And you can see that because of the spacing of the elements, right? And when you're writing the matrix, try not to write the elements close to each other. So it gives a different interpretation. You must write your elements with space, and the spacing between the elements differentiate the rows and the columns. Okay, guys? So remember that. So this matrix would have 4 rows, but all these elements are in 1 column. So it would be a 4 by 1 matrix. 4 rows, 1 column. So the order or the size of this matrix D would be a 4 by 1. I hope, guys, that you would have understood the order of a matrix and how to tell the order of a matrix, or how to write the order or the size of a matrix. Okay, once you can write the order or size of a matrix, therefore means that you would have comprehended all of that, right? Now, the next concept as it relates to the matrix is the arrangement or position of each element in the matrix. Now, guys, as you can see, all these matrices up here, they have elements, right? And the elements, each of these elements are in a specific position. And you, as the student, should be able to tell which position each element is in within the matrix. Now, because within the matrix, the elements are arranged into specific rows and columns, we can tell what is the specific position or location of an element within the matrix. So let us take, for example, the matrix A and the element small a here. Let us see what's the position of that element. So element A is positioned in the first row and first column. Do you agree with that, guys? So let us look at element A. So we agree that element A is in the first row. That is the first row of the matrix, right? So element A is in the first row. However, it is also in the first column. So the specific position of element A would be first row, first column. Everybody agree with that so far? So element A is in the first row and the first column. All right, let us now look at element B. So element B, guys, here's element B. Element B is also in the first row. We agree with that. However, it is in the second column. So the specific position of element D would be the first row, second column. That's the position of element D, guys. So if I were to ask you which element is in the first row and the second column, your answer should be B. Okay, guys. Now let us look at element C. So element C is, here's element C. So element C would be positioned in which row, right? So we tell the row first, we tell the row. So it is in the second row. However, it is in the first column. So element C would be in the second row, first column. All right, guys? That's the position of element C. And element D, of course, there's element D. Element D would be in the second row, right? Second row. However, it is in the second column. So element D is in the second row, second column. So guys, I hope that would have been clear to you. It's pretty simple, guys, nothing difficult to tell the position of each element within the matrix. And just to remember that the order of the matrix, you tell the row by the column. And when you're writing it, you write the number of rows first, followed by the number of columns. Do not write the number of columns first and rows last. It must be rows first, columns last. Okay, guys? So, quick recap. For example, B here, matrix B, right? It has 2 rows. So we write the 2 here. However, these elements are in 1 column, so we write the 1 here. So you always write the rows first and the number of columns last. Number of rows first, number of columns last. Okay, guys, I think that is explicitly clear. All right, so let us move on to the next slide. So here's an activity for you guys. So this activity is for you. You can actually pause the video and do this activity. It is based on the concepts that we previously looked at on the slides before this one, right? So doing this activity will give you an idea as to whether you would have learned what we did just now. Okay, guys, so pause the video, do this activity, and see what your scores are, okay? So this, it says in number 1, state the order size of the following matrices. So remember, guys, that matrices is plural, right? And matrix is singular. So from time to time, you will hear me interchange the words based on what I am saying. So remember, matrices is plural and matrix is singular. Okay, guys? That's the only difference. One is the plural form, one is the singular form. All right? So 1 matrix, 2 matrices. Okay. All right, so do this activity, guys. It's pretty easy. All you need to do is tell what is the order or the size of matrix P, the order or size of matrix T. So we have 2 matrix, 2 T's here. And you have to tell the order or the size of each of them. And we have matrix M, so we're to tell the order, the size, and we also have another matrix here at number V, or number 5. So you're to tell the order of those matrices. All right, guys, that should be a simple activity. So complete that activity, and you can share your answers with me by posting below the video. Okay, guys, or you can contact me or reach out to me. All right, so given the matrix, number 2, given the matrix E, right, you're supposed to tell the position of the element Y, you're supposed to tell the position of the element 4, you're supposed to tell the position of the element -8, you're supposed to, and in 4, you're supposed to tell the position of the element X. All right, guys, again, if you need to revisit the previous slides and recap, please do so. but these two activities are pretty straightforward, and they're based on the slides we covered previously, right? So you can go back and watch those slides and then come back to this activity and complete it. But it's pretty easy, guys. All right, all the best on that activity. So our next topic is how to formalize a matrix. Now, guys, as the term suggests, formalize, right? That is saying, how do we form a matrix? How do we form a matrix? Formalizing a matrix is basically saying, how do we form the matrix, guys? Remember now that, you know, this representation here of elements in a pair of curved or square brackets didn't drop from the sky, guys. We didn't pick it out of a hat. It actually came from data, right? So this representation of the matrix came from some data that was organized, for example, in a data table, right? And we know that tables naturally have rows and columns, right? And so if we have some information or some data about a particular event or a particular study or something, we could consider representing that data or information in matrix form, guys, right? Because once we can tell what is in which row and what is in which column, then we can express that from our table in matrix form. So formalizing a matrix is just basically putting into perspective, giving you an idea that a matrix came from somewhere, right? We didn't just pull it from a hat. It came from somewhere. And one possibility where that matrix could be derived from is from a data table having some information pertaining to real life events, okay? So here, for example, Betty's lunch order for the first 3 days of school for week 1. So this data table is showing Betty's lunch order for the first 3 days of school in week 1, right? So we can see that there's a row having the number of patties that she bought or she had for lunch, and row 2 showing the number of sodas she had. However, the columns are showing the days in which she had these items, right? So this data could easily be represented as a matrix, guys. And when it is represented in a matrix form, you know what this column this row represent, right? This row represent the number of patties that she would have bought on a Monday, Tuesday, and a Wednesday, right? And this row here would represent the number of sodas that she would have had for each of those days. So in matrix form, you can still put meaning to the data once you know where it is coming from, right? And we know that this matrix is coming from this data table, and this matrix is coming from this data table. And it is so simple, guys, because the table is already organized in rows and columns. So in representing the table in matrix form, right, whatever is in the rows of the table would be placed into the same row when you're writing it as a matrix. So here in this row from the table, we have 2, 1, 3. So when you're writing it in matrix form, that row will be placed in the same position in the matrix, row 1, right? And row 2, which is 1, 0, 2, will be placed in row 2 within the matrix. And the same for column 1, 2, 1 would be placed in column 1, and 1, 0 would be in column 2, and 3, 2 would be in column 3. Okay, guys, so that's how you pretty much form a matrix from a table by putting the elements in the rows and the columns exactly in the matrix in the same position. However, in the matrix, you are now using space to separate the rows from the column. versus in the table, you'd have the lines clearly showing you the different rows and columns. So this is how you formalize a matrix, guys. Matrix is not pulled from a hat. It was actually formed from real data. For example, data expressed in a table, we could easily translate that to a matrix. For example, B week 1 and B week 2. Okay, guys. So let us now look at some important types of matrix. Right? Some important types of matrix. So the first one we have is a row matrix. Right? Very important, guys. You need to know these types of matrix because you know they're going to come in very handy, especially later on in the other parts of the matrix lessons. So row matrix, basically a row matrix only has one row. That's the definition, guys. Row matrix is a matrix having only one row. For example, here's a matrix having one row. So any matrix that has only one row is a row matrix, right? And please, we do not put a comma. We do not put commas between the elements. No, we do not. We're not representing coordinates, guys. So we do not put arrows, not arrows, commas. We do not put commas between the elements. Okay, please don't do that. So this would be our row matrix, right? Row matrix. Those are our row matrix here. Okay, guys. Let's look at the next one now, column matrix. So a column matrix is a matrix having only one column, right? So a row matrix has only one row. A column matrix is a matrix having only one column. Example. So look at example B here. We can clearly see that this matrix only has one column. See, we draw a vertical line through the elements, we get only one column. And here we also get one column again. So this matrix would be a column matrix, right? And it only has one column, right, guys? This is a column matrix, right? When you start to do vectors, you'll also learn that a column matrix, right, is a column vector, right? That a column matrix is also a column vector. However, just know that a column matrix has only one column. Okay, guys? So let us now look at our square matrix. So a square matrix is a matrix having equal number of rows and columns. So the square matrix, guys, the square matrix has equal number of rows as columns. So a matrix having 2 rows and 2 columns would be a square matrix. A matrix having 3 rows and 3 columns would be a square matrix. A matrix having 4 rows and 4 columns would be a square matrix. So a square matrix is a matrix having equal number of rows and columns. So the number of columns is equal to the number of rows. So in this example, you can see that there are 2 rows, right? And there are 2 columns. So that would be a square matrix. Now, a diagonal matrix is a type of square matrix. So first we establish that a diagonal matrix is a type of square matrix where all the elements are 0 except the leading diagonal elements. So a diagonal matrix is a square matrix, first of all. So that means it must have equal number of rows and column. But the differentiating factor now is that all the elements are 0 except the leading diagonal elements. Now the leading diagonal elements runs from upper left to lower right. So in a matrix, guys, this is a key term you need to learn, leading diagonal elements. We're going to look at that again further on in the other parts of matrices, leading diagonal elements. So in a matrix, the leading diagonal elements, and I should say in a square matrix, the leading diagonal elements run from upper left to lower right. Upper left to lower right. Okay, guys? So The diagonal matrix is a square matrix. That means it has equal number of rows as columns, right? However, what makes it diagonal is that the leading diagonal elements must not be zero. So all the other elements can be zero except the leading diagonal elements. Now, let us look at example A. So we say that the leading diagonal elements run from upper left, so I'm circling it here, upper left to lower right. So you can see that this part of the matrix is the upper left, and this part down here is the lower right. So it means that this would be the diagonal elements, right? 2 and 6. However, all the other elements must be zero. So clearly this would be a diagonal matrix because the diagonal elements are not zero. However, all the other elements are zero. Let's look at example B. Can we identify the leading diagonal here in matrix B? Of course. Remember now, matrix B is a square matrix because a diagonal matrix has to be a square matrix, right, guys? So this matrix B here has equal number of rows as columns. However, it is a diagonal matrix because the leading diagonal elements, here are the leading diagonal elements, guys. The leading diagonal elements are not zero. They are not zero. However, all the other elements must be zero. So you can see 4, -1, 3. Those numbers are not zero. So the leading diagonal elements must not be zero. However, all the other elements must be zero. Right? So that's how we define a diagonal matrix. All right, guys? And now we move to our identity matrix. So in terms of identity matrix, we have to be careful because we can have an identity matrix for multiplication as well as we can have an identity matrix for addition, right? So the identity matrix for multiplication is a type of diagonal matrix where the leading diagonal elements are all 1. So the identity matrix for multiplication now, we normally use the letter I, capital I, to name an identity matrix, right? So to name an identity matrix, we normally use the letter I, capital I. So the identity matrix for multiplication now is a type of diagonal matrix. So the identity matrix for multiplication is a type of diagonal matrix. What do we mean by diagonal matrix? 1, it must be a square matrix, and 2, the leading diagonal elements must not be zero. However, all the other elements must be zero. So the identity matrix for multiplication is a type of diagonal matrix which satisfies those criteria I just made mention of, where the leading diagonal elements now are all 1. So it would be a diagonal matrix because the leading diagonal elements are not zero, right? However, what makes this diagonal matrix the identity matrix is because the diagonal elements are 1. So it fits the description of a diagonal matrix because the leading diagonal elements are not zero. However, all the other elements are zero, right? However, it becomes an identity matrix for multiplication now because the leading diagonal elements are all 1. So the elements have to be 1, right? Nothing else. So if you look at it, on these diagonal matrices up here, you'll realize that, let me clear. If you look at these diagonal matrices up here, you'll realize that the leading diagonal elements here are not zero. And if you look at the identity matrix for multiplication, you realize that the leading diagonal elements are not zero. However, the difference between the diagonal matrix and the identity matrix, the simple difference is that the identity matrix, the leading diagonal elements are 1. They must be 1. All the elements in the leading diagonal must be 1 for the identity matrix for multiplication. So the identity matrix for multiplication is still a diagonal matrix, right? It is a diagonal matrix by definition. However, it becomes the identity matrix for multiplication because the leading diagonal elements are 1. However, a diagonal matrix in general, the leading diagonal elements must not be 0. They can be any number. They could be 1, as in the case of the identity matrix of multiplication. They could be 2 and 6. It could be 4 negative, negative 1, 3, any other number, once those numbers are not 0. However, even though the leading diagonal elements are not 0, for it to be a diagonal matrix, the other elements now must be 0. The other elements must be 0, as you can see here. Right? So the identity matrix for multiplication is 1, 0, 0, 1. 1, 0, 0, 1. And please make note of that identity matrix here. This identity matrix, you will see it again, right? It is the identity matrix for multiplication, and it is 1, 0, 0, 1. The leading diagonal elements are 1. That is why, that is what makes it the identity matrix for multiplication, right? Let's move to the identity matrix for addition or subtraction. Now, the identity matrix for addition or subtraction is clearly different from the identity matrix for multiplication, right? Because the identity matrix for addition or subtraction is just basically a matrix. It's not a diagonal matrix. It's not a specific type of matrix. The identity matrix for addition or subtraction is just any matrix, guys, where all the elements are 0. So if all the elements are 0 in a matrix, it means that it is the identity matrix for addition or subtraction. That pretty much means that if you should add this matrix to another matrix, or if you should add the identity matrix, not this one specifically, but any, if you should add an identity matrix, right, to another matrix of similar order or size, or subtract it, you will get back the original matrix. So that's why it is called identity, right? So to explain that, let us say we have the number, let's say we have the letter A, right? And we should add A to 0. When we add A to 0, we're gonna get back A. So it means that 0 is the identity number for addition. So it's the same kind of thing with matrices, is that if we have the identity matrix for addition or subtraction and we add that to a known matrix, right, the result will be the known matrix, right? And for multiplication, this matrix here, 1, 0, 0, 1, is a square matrix, which is the identity matrix for multiplication, is pretty much saying, if you should recall, that 1 is the identity number for multiplication. So if I have the letter A and I multiply A with 1, I'm going to get back A, right? So 1 is the identity number for multiplication. And that is why the identity matrix for multiplication has 1 in the leading diagonal elements. So when you multiply this matrix with another 2 by 2 matrix, you're gonna get back that matrix. So that is why this is called the identity matrix of multiplication, right? It gives you back the matrix that you multiplied with. And this one is the identity matrix for addition. That means if you add a identity matrix for addition or subtraction to a matrix, to a specific matrix, you're going to get back that matrix. In other words, guys, let me just do a quick scenario here. So for example, if you have the matrix 2, 1, right, and you add that to the identity matrix 0, 0, what you're going to get back? You're going to get back 2, 1, right? So that's basically what I'm saying. It is the identity. So 0, 0 here would be the identity matrix for this matrix, right? So this would be a 2 by 1 matrix, and the identity matrix must also be a 2 by 1, and the elements in there must be all 0. Okay, guys, so that's pretty much what I'm saying as it relates to the addition, the identity matrix for addition and subtraction, right? And for multiplication, it is pretty much saying that if I have the, if I have the matrix 1, 0, 0, 1, and I multiply that to 1, 2, 3, 1 to another matrix like that, it means that I'm going to get back the matrix that I multiply the identity matrix to, which is 1, 2, 3, 1. That's all it is saying, guys. So we will look at that in more detail when we start to look at multiplication of matrices. All right, guys. So that is it for types of matrix. I hope it would have been clearer, or it would have been clear for you, these types of matrix. You can always go through the video and rewatch the explanation, guys, so you understand clearly these different types of matrix. So the final thing that we will do is an activity. So we have an activity 2 for you guys. So you're going to complete this activity, pause the video, complete the activity, guys, and share your answers, your responses to these questions. So this would be a pretty easy activity, guys, because it is based on what we covered on the slides just now. Okay, so this should be a pretty easy activity for you. So basically, you're going to form a matrix from the data table here. So you're going to form a matrix. You can give it a name. You could call it matrix C or matrix A. However, the elements in the matrix must be the same for everyone who is doing this question. All right. So the elements must be arranged in the same way for your answer. Okay. For example 2, name the specific type of matrix shown. So all you're gonna do is just look at these matrices, guys, and tell which one is a square or a row matrix or a diagonal matrix or identity matrix for multiplication or identity matrix for addition, whatever. Just look at them and tell what type of matrix they are. Okay, so pretty much, guys, this would be the end of matrices part 1. I do hope I was able to shed some light on the concept of a matrix, that is, what is a matrix and the different features of a matrix, as well as formalize a matrix, where a matrix came from and how we can form it, especially from tables and so forth. And we'll also look at types of matrix. Thank you, guys, for watching, and please like and subscribe to this platform. Thank you so much. See you in part 2.